Welcome to Num Academy CET Coaching Classes 2020. Behind every medicine, there is a huge contribution of chemistry. Now, let us start discussion about the subject chemistry, and the topic is states of matter from first PU. States of matter. Synopsis. Change in state. It is overall effect of intermolecular forces, molecular interactional energy, and thermal energy. Measurable properties of gases. Pressure, volume, temperature, number of moles, viscosity, specific heat are some of the measurable properties. Three states of matter. Matter is classified into three states. First one is solid state, second one is liquid state, and third one gas state. Gas laws. The gas laws which we will study now are the result of research carried on for several centuries on the physical properties of gases. The quantitative relationship between any two of the variables, that is volume, number of moles, pressure or temperature, when other two are kept constant. Boyle's law. The pressure of fixed mass of gas varies inversely with the volume at constant temperature. Pressure is inversely proportional to volume when number of moles and temperature are kept constant. P1 V1 is equal to P2 V2. Charles' law. At constant pressure, the volume of fixed amount of gas varies directly with its absolute temperature, that is, V is directly proportional to T, or V by T is equal to constant. V1 by T1 is equal to V2 by T2. Gay-Lussac's law. At constant volume, the pressure of fixed amount of gas varies directly with its absolute temperature, that is, P is directly proportional to T, or P by T is equal to constant. P1 by T1 is equal to P2 by T2. See the given diagram. The Boyle's law, P1 V1 is equal to P2 V2. The Charles' law, P1 by T1 is equal to P2 by T2. The combined gas law, P1 V1 by T1 is equal to P2 V2 by T2. Finally, the ideal gas law, PV is equal to nRT. Ideal gas equation. The relationship between pressure, volume and temperature by gas laws given by PV is equal to nRT. Avogadro's law. At given temperature and pressure, the volume of gas varies directly to the amount of gas. That is, V is directly proportional to the number of moles when pressure and temperature are kept constant. Dalton's law of partial pressure. The pressure exerted by a mixture of non-reacting gases is equal to the sum of their partial pressures at constant volume or temperature. Kinetic molecular theory. Total pressure is equal to sum of the individual pressures when temperature and volume are kept constant. Kinetic molecular theory. First one. Gases consist of large number of identical particles, that is atoms or molecules, that are so small that the actual volume of the molecules is negligible in comparison to the empty space between them. Second one. There is no force of attraction between the particles of a gas at ordinary temperature and pressure. Third one. Particles of a gas are always in constant and random motion. Fourth. Pressure is exerted by the gas as a result of collision of the particles with the walls of the container. Fifth. Collisions of gas molecules are perfectly elastic. Sixth. At any particular time, different particles in the gas have different speeds and hence different kinetic energies. Seventh one. Average kinetic energy of the gas molecules is directly proportional to the absolute temperature. Real gases. The gases which deviates from ideal behavior at higher pressure and low temperatures because of force of attraction between molecules increases. Compressibility factor, denoted by Z. It determines extent of deviation of real gases from ideal gas behavior. That is, Z is equal to PV by nRT. For ideal gas, Z is equal to 1. For non-ideal gas, Z is less than 1 and Z is greater than 1. Van der Waals equation, that is P plus n square A by V square into V minus n into B is equal to nRT. Critical temperature, denoted by Tc. the temperature above which a gas cannot be liquefied, whatever high pressure may be. Critical pressure, the minimum pressure required to liquefy a gas at its critical temperature. Critical volume, the volume of 1 mole of gas at critical temperature and critical pressure. Supercooled liquids, the liquids which are cooled to a temperature below its freezing point without freezing. Van der Waals equation, P plus n square A by V square into V minus NB is equal to nRT, where P denotes measured pressure, n square A by V square denote adjust the P up, V denotes measured volume, and B adjusts the volume down. Elastic collision, the collisions in which no loss of kinetic energy, only there is transfer of energy. Vapor pressure, the equilibrium pressure by vapor of liquid in a container at given temperature T. At higher altitude, the boiling point of water decreases because the atmospheric pressure is less than 1 atmosphere. Surface tension, denoted by V, it is force acting per unit length perpendicular to the line drawn on the surface. Unit is Newton per meter. It decreases with increase in temperature. It increases with increase in external pressure. Because of it, falling drops of liquid are spherical, and also liquid in capillary tube rises. Viscosity, denoted by neta, it is resistance offered to the flow of liquid due to friction between layer of liquids. F is equal to N into A into dV by dN. Effect of temperature and pressure on viscosity. It decreases with increase in temperature and increases with increase in pressure. Low melting point and boiling point of molecular liquids is due to low magnitude of molecular interaction energy. Let us discuss some of the questions. First question, what is value of Boyle's temperature of ethane gas when A is equal to 5.489 decimeter power 6 atmosphere mole per square and B is equal to 0.0638 decimeter cube atmosphere per mole? Option A 1048 Kelvin, option B 104.8 Kelvin, option C 209.6 Kelvin, option D 290.6 Kelvin. The answer is option A 1048 Kelvin. Now let us discuss how to solve the problem. We know that Boyle's temperature, that is Tb is equal to A divided by R into B, given that A is equal to 5.489 decimeter power 6 atmosphere per mole square, B is equal to 0.0638 decimeter cube atmosphere per mole, and R is equal to 8.314. Substituting all the given values, we get Boyle temperature of ethane gas is equal to 1048 Kelvin. Second question, volume of universal gas constant R depends upon the option A temperature of the gas, option B volume of the gas, option C number of moles of the gas, option D none of this. And the answer is option D none of this, as universal gas constant does not depend on none of the parameters, and also it is independent of all of the parameters. It does not change with any change in the parameter. Third question, the Boyle's temperature for the ideal gases is given by option A by R, option B A by BR, option C 2A by BR, option D none of these. The answer is option B A by BR, as we have discussed in the first question. Fourth question, the ratio of Van der Waals constant A and B has the dimensions of option A atmosphere per mole, option B liter per mole, option C atmosphere liter per mole, option D atmosphere per mole square. And the answer is option C atmosphere liter per mole. Fifth question, at extremely low pressure, the Van der Waals equation for 1 mole of a gas may be written as option A PV is equal to RT plus PV, PV is equal to RT minus A by V, option C PV is equal to RT, option D P plus A by V into V minus B is equal to RT. And the answer is option B PV is equal to RT minus A by V. Sixth question, the compressibility of a gas is less than unity at STP. Therefore, option A, Vm is greater than 22.4 liter, Vm is less than 22.4 liter. Option C, Vm is equal to 22.4 liter. Option D, Vm is equal to 44.8 liter. And the answer is option B, Vm is less than 22.4 liter. 7th question. The correct order for magnitude of van der Waals constant B should be option A, C2H6 is less than CO, less than CO2, less than helium. Option B, CO is less than C2H6, less than He, less than CO2. Option C, C2H6 less than CO2, less than CO, less than He. Option D, He less than CO, less than CO2, less than C2H6. And the answer is option A, C2H6 less than CO, less than CO2, less than He. 8th question. If temperature T2 greater than T1, which graph of Maxwell-Boltzmann distribution of molecular speed is correct? And the answer is option B. 9th question. An ideal gas cannot be liquefied because option A, the intermolecular force of attraction between the gaseous molecules are negligible. Option B, its critical temperature is very high. Option C, the van der Waals constant A and B are very high. Option D, all of this. And the answer is option A, the intermolecular force of attraction between the gaseous molecules are negligible. The values of A for the gases O2, CO2, N2, CH4 are respectively 1.36, 3.64, 1.39 and 2.253 liter square atmosphere per mole. Which gas can be most easily liquefied? Option A, O2, option B, CO2, option C, N2, option D, CH4. And the answer is option B, CO2. As the value of A increases, the easily is the liquefied gas. Thank you.